So this is lecture 1 of the electronics course, and in this lecture we are starting with the first module. It's probably the shortest and one of the easiest modules of this course. So this has to do with what we call network theorems. If you want to read more about network theorems, you can look at the suggested literature. You can look at Malvino chapter 1. And you can also look at Eggleston chapter 1, and of course some other resources as well that you might find online. Before we start with this, I just want to brush up quickly on some basics of electronics which you might have studied in your 11th and 12th standard. We all know what a resistor is, and if you want to find out what is the potential difference across this resistor, then you know that this is I times R, where I is the current that's flowing through this resistance. So for a resistor, V and I are always proportional to each other. So this is called an ohmic device with the voltage and the current in direct proportion, and the constant of proportionality is the resistance. I also want to remind you what a constant voltage source is. This is a source, as the name suggests, which offers you a fixed voltage. So you can connect this to some kind of circuit over here. Doesn't matter what's in this. You can have resistors, etc. All kinds of elements. The voltage, the potential difference that the source provides across these two ends will always be constant. No matter what you're doing inside the circuit, depending on what the elements in the circuit are, the current flowing through the circuit might change, but the potential difference across this will always remain the same. That's why constant voltage source. And the ideal resistance of a constant voltage source is 0. Ideal internal resistance. Now, since we've talked about a constant voltage source, let's also talk about a constant current source. This one will always provide you with a fixed current, I. So once again, this you can connect to some circuit with all kinds of elements, and depending on what elements you have inside this circuit, the potential difference might change, but the current flowing through this wire will always remain the same. And for a constant current source, the ideal internal resistance is always very large, tends to infinity. So these are some quick basics of voltage sources, current sources, and resistors. And we will use these in what is to come. Now, the next thing I want to remind you of is what is called Kirchhoff's laws. So Kirchhoff has two famous laws in electronics. The first one is Kirchhoff's current law. What this says is that suppose somewhere in your circuit you have a junction. So a junction is just a point where lots of wires are coming and meeting in one point. And some of these wires are bringing current into this junction, and some of them are taking current out of this junction. Then what Kirchhoff's law says is that the sum total of all the currents entering is exactly equal to the sum total of all the currents leaving this junction. So in terms of this diagram over here, I1 plus I2 plus I3 equals I4 plus I5. What does this mean physically? Current is basically just a flow of charge, right? So any charge that is entering this junction has to eventually leave it, because this is not some Harry Potter world where charge can suddenly just disappear into nowhere. So any charge which enters the junction must eventually leave, and that is precisely what this current law is saying. So Kirchhoff's current law is just, in some sense, a restatement of the conservation of charge. Similarly, there is something called Kirchhoff's voltage law. And what this law says is that suppose you have a circuit. So here is a source of potential difference or EMF. And let's put some resistances over here. And so across each of these resistors, there will be some potential difference. So let's say the potential difference across this is V1, across this one is V2, and across this one is V3. Then what Kirchhoff's voltage law says is that E must be equal to V1 plus V2 plus V3. Now, what does this mean physically? This is just a statement of conservation of energy, because potential difference is basically just a measure of the amount of work that the cell has to do to push current through this resistor over here. So if the cell wants to pass electrons through the first resistance, it has to cross a potential difference of V1. So the total EMF across that is generated by the source is just the sum total of V1 plus V2 plus V3. So Kirchhoff's voltage law is just a restatement of the law of conservation of energy. So these are two of the basic laws that we will use extensively and that I wanted to remind you before we start this course. So these are sometimes abbreviated as KCL and KVL. You might find this notation in some of the books that you read. Right, so those are the basics. Now we can start discussions about the actual network theorems that we wanted to study in this course. So the very first theorem that we are going to look at is what is called Vennens Theorem. I'm not sure if some of you have already studied some amount of electronics in your 11th and 12th standard. Maybe if you had a specialization in electronics, you might have come across these before. But anyway, it's always a good idea to recap it. So these network theorems are basically tools which make it easy for us to analyze complicated circuits. And because the circuits that we're going to be studying in this course are going to get more and more complicated, it's useful to get these tools, these very handy tools ready in the beginning. So here's what Thevenin's theorem says. Suppose you have some complicated circuit, some network. And let's say this network has these two output terminals. Let's call them A and B. So this is where you're going to measure the output. So typically the way to measure the output is to connect some kind of resistance across this, and this is called the load resistance. So Thevenin's theorem says that if you have some complicated circuit like this, you can write an equivalent circuit of the following form. So you have one voltage source and one resistance in series with it. This voltage, we call it the Thevenin voltage. This resistance which is in series with it, we call the Thevenin resistance. And all the properties that you might measure across RL, like the potential difference or the current, will remain the same. So question is, how do you calculate what the Thevenin voltage and the Thevenin resistance for this complicated network should be? So the way to do that is as follows. There are two steps. So the first step is you remove the load resistance and then you calculate the open circuit voltage across AB. And this voltage is what will be VTH. And the second step is you remove the load voltage, the load resistance, and you replace all the sources with their internal resistances. As we saw before, internal resistance of an ideal voltage source is 0. Internal resistance of an ideal current source is infinite. So you replace the sources with those ideal internal resistances, and then the effective resistance across AB is what we call the Thevenin resistance. So this is the procedure for calculating Thevenin voltage and the Thevenin resistance. Let's take one concrete example to see how we apply this theorem. So let's look at the following circuit. So let's say we have a source which gives voltage E, and let's say we have resistances R1 and R2, and I'm going to measure the output across R2. So this is actually not a very complicated circuit, it's quite simple, and you don't really need Thevenin's theorem to solve it, but we're just using it as an illustrative example. So let's see what we get. So in step 1, what was that? You first remove the load resistance and you measure the voltage across AB. So in doing that, your circuit will look something like this. And you want to measure the voltage across these 2 points over here. Well, how do you do this? So the current flowing through this circuit is going to be E divided by R1 plus R2, because these two R1 and R2, these two resistances are in series, and there's no current flowing through A and B because you have opened that load resistance over there. So this part is as good as not there. So this is just E flowing through R1 and R2 in series. So effectively the resistance over here is R1 plus R2. So the current flowing through the circuit is E divided by R1 plus R2. And so the voltage across R2 or across AB equivalently is just I times R2, which is E divided by E R2 over R1 plus R2. And this is what we call the Thevenin voltage. Step 2, we want to find what is the Thevenin resistance this time. So once again we remove the load resistance, and now we replace the voltage source with its internal voltage, its internal resistance, which is 0. So what we have is this. And we want to find the effective resistance across AB. Now you will notice this is just R2 and R1 in parallel with each other, because this is, you can just redraw it and it will look like this. So the effective resistance across these two terminals, which is the Thevenin resistance, is just R1 parallel R2. Do you know this notation, by the way, R1 parallel R2? So normally if you have two resistances in parallel, then the effective resistance is 1 over R1 plus 1 over R2. And if you solve this, you will get R is R1 R2 divided by R1 plus R2, or what is sometimes called product divided by sum. So the compact notation for writing this is R1 parallel R2. This is just notation that's easy to use instead of writing R1 R2 divided by R1 plus R2. So this is the Thevenin resistance. So that's it. Your work is done. All you need to do now is you set up a circuit which has VTH of this value, ER2 divided by R1 plus R2, and then connect it in series with RTH, which is R1 parallel R2. And now if you want to measure, let's say, the current flowing through the load resistance or the potential difference across the load resistance, then it is just this simplified circuit that you need to analyze. You don't have to look at this complicated circuit anymore. By the way, just one notation that a terminology that I want to introduce over here. This circuit is often referred to as a voltage divider circuit. And the reason it's called a voltage divider circuit is this formula right here. So if you look at the potential difference across AB, you will find that this circuit divides the potential difference which the cell has provided, which is E, into the ratio R2 divided by R1 plus R2. So if you just change the values of R1 and R2, then you can adjust the ratio of R2 divided by R1 plus R2. And by doing that, you can adjust how much potential difference you're getting across these terminals A and B. So this is called a voltage divider circuit, and we will also use this at some point in the future. So this is what Thevenin's theorem tells us, that you can find this kind of Thevenin equivalent circuit which simplifies your calculations. Now, the next theorem that we are going to be looking at is what is called Norton's theorem. Norton's theorem is in some sense similar to Thevenin's theorem. Once again, we start off with some complicated circuit. And this has again output terminals A and B. So we want the output over here, and we might connect a load resistance across these two terminals. And question is now, how do we analyze this? So Norton's theorem says that you can simplify this complicated circuit and you can draw the Norton's equivalent circuit for this, which consists of a constant current source this time, and this provides a current called the Norton current. And with this, you have a resistance in parallel, and this is called the Norton resistance. And then, of course, you have the load resistance over here. So any complicated circuit can be simplified and drawn into a Norton's equivalent circuit. So question is, what are the values of Norton current and Norton resistance? That's what we want to find out. Once again, there are two steps for doing this. Step 1, open the load resistance. Sorry, this is Norton. So now you want to, so remove the load resistance and short the terminals AB. Basically, you replace this load resistance by a zero resistance, and then you find the current through this short. So this current that you find, this is IN. And then once you've done that, you want to find what is the Norton resistance. Well, this is going to be the same procedure as in the Thevenin case. So you open the load resistance, replace all the sources with their internal resistances, and you calculate the effective resistance across AB. And this effective resistance is your Norton resistance. So this is Norton's theorem. This tells you how to calculate the Norton current and the Norton resistance. Let's again take an example for this one as well. And we will once again use our old friend, the voltage divider circuit. So here is the voltage divider. And this is where I want to measure my output. So I'll put my load resistance over here. So I want to find the Norton equivalent circuit for this network. So step 1, we are going to first remove the load resistance and short these two terminals, short AB over here. So we get E, R1, R2, and this gets shorted. And I want to find what is the current flowing through AB. This is now straightforward. If you look at this circuit, so the current is going to flow this way. Once it comes here, it has two paths. It has one path which has some resistance, some finite resistance, and it has one path through AB which has zero resistance. So the current is always going to pass through this zero resistance. Basically, this R2 doesn't matter at all. You can also look at it one more way. You can see that this part of the circuit is R2 parallel 0, which is just 0. So basically the presence of R2 doesn't matter over here. This is just R1 in the circuit. So the current through this path AB is just going to be E divided by R1. If in case that wasn't clear, it's because the circuit now looks like this. So current is just E divided by R1. So that was step 1. We have this is the Norton current. Now we want to find the Norton resistance. Once again, this is the same calculation as before. We replace the voltage source with 0 because that's its ideal internal resistance. And we find the effective resistance between these two terminals. And as we have seen before, this is just R1 parallel R2. So we know what the Norton current is, we know what the Norton resistance is, and all we need to do now is put them together. So we will put this ideal current source IN. In parallel with it, we will put RN, and then we will connect the load resistance. So if you want to calculate the current across the load resistance or the potential difference across the load resistance, you can use the simplified Norton's equivalent circuit instead of using this complicated original network. So that's Norton's theorem for you.